Hi, my name is Isabella Enciso, and I'll be presenting this problem today. So the problem states that water is pumped from the large tank shown in diagram A below. The entrance to the pipe section is sharp edge and the pipe is cast iron with a total length of 2 meters. Flow within the pipe is observed to be fully turbulent. The relationship between volumetric flow rate and the actual head rise is provided in the pump specifications and is shown in diagram B. So in part A, we have to determine the volumetric flow rate for the system. In part B, we have to show that the observation of fully turbulent flow was correct, and in part C, if the pump is 70% efficient, determine how much power must be supplied to the pump. So to start off, we're going to take out information from the prompt given to us that is important. So we're given that the pump is cast iron, and since the pump is cast iron, we can go to table 8.1 in the textbook and look up the equivalent roughness of cast iron, which is 0.26 millimeters. We are also given the length, which is 2 meters, so we know that L is equal to 2 meters. And we're also given that the section is sharp-edged. Based on this information, we can look in the textbook, and anything that is sharp-edged will have a head loss coefficient of 0.5. And looking at diagram B, over here, we can see that the head rise equation given to us is that head rise is equal to 20 minus 2,000 Q squared. So to begin part A, we are looking for Q. Now we know that volumetric flow rate Q is equal to VA, velocity times area. So to begin, we're going to label our points on the diagram. So we're going to label point 1 here and point 2 at the exit. And from here, we're going to be using the pump performance equation, which is P1 over specific weight plus V1 squared over 2G plus Z1 plus head rise is equal to V2 is equal to P2 over specific weight plus V2 squared over 2G plus Z2 plus head loss. Now looking at these points here, we can see a point 1 that is open to the atmosphere, so that means P1 0, but it's also at the very top, so we know V1 is going to be about 0, so V1 becomes 0. And point 2, it is also open to the atmosphere here, so that becomes 0. However, it is coming out with velocity, so velocity 2 is going to be a variable we need to solve for. However, it is 6 meters below point 1, as stated here, which means Z2 is going to be 0. So from here, we have Z1 plus head rise is equal to V2 squared over 2G plus head loss. So looking here, we're going to solve in terms of V2 because we know that Q is V times A. So that means we can plug this equation back into here. So we know that H head rise is equal to 20 minus 2,000 V2 A2 squared, which means head rise is going to equal to 20 minus 2,000 V2 squared A2 squared. And that could be substituted back into here. Now for head loss, we know that it is the friction factor times L over D plus the head loss coefficient times V squared over 2G. And for this one, it's going to be V2 squared. So we know that the relative roughness is 0.26. And we know the diameter of the pipe is 0.07 meters, which is 70 millimeters. So when we do that, we get 0.0037. Now, if we use the Moody diagram and we draw a line to the friction factor, we get a friction factor of about 0.026. So we can plug that all back into here. So we get that head loss is equal to 0.026 times 2 meters divided by 0.7 meters for diameter plus 0.5 times V2 squared over 2G. And when that is simplified, you get that head loss is equal to 1.24 times V2 squared over 2G, and that can be plugged in as well. And we know that Z1 will be 6 meters because of the height given to us here. So using all this information, we will rewrite the equation as 6 plus 20 minus 2000 B2 squared A2 squared is equal to V2 squared over 2G plus 1.24 V2 squared over 2G. Now we know the value for G and area, so we'll plug those values in and solve for V2 squared. So we add these two here. You have 26 minus 2000 times V2 squared times pi over 4 times 0.07 squared, and this entire thing is squared, is equal to V2 squared over 2 times 9.81 for gravity plus 1.24 times V2 squared over 2 times 9.81 for gravity. So when we simplify this in our calculator, we get 26 minus 0.0296 V2 squared is equal to V2 squared over 19.62 plus 1.24 divided by 2 divided by 19.62 V2 squared. So you get 26 minus 0.0296 V2 squared is equal to 0.11462 V2 squared. From here we add 0.0296 V2 squared to both sides. So you end up with 26 is equal to 0.14116 V2 squared. Divide both sides by that. 0.14116, and you get 184.18 is equal to V2 squared. You take the square root of that, and you get that V2 is equal to 13.57 meters per second. Now using this information, you can plug this value back into Q, where Q is equal to V2A2. So from here we can say that Q is equal to 13.57 meters per second times pi over 4, 0.07 meters squared for area. And from here we get that Q is equal to 0.052 meters cubed per second. And that is our first answer. For part B, we needed to find, we have to show that the observation of that observation fully turbulent flow was correct. So now that we have the volumetric flow rate and velocity, this is possible. So for part B, we need to find the Reynolds number, and we know that the Reynolds number is equal to rho VD divided by mu, where rho is going to be the density of water of 999 kilograms per meters cubed, which is found in our table in the book, times the velocity, which we just found to be 13.57 meters per second, times the diameter, which is given to us of 0.07 meters, divided by mu, which is 1.12 times 10 to the negative 3 newtons per second per meter squared, which is also found in the table in the book. And when we do this, we get a Reynolds number of 8.47 times 10 to the 5th. And if we look on the Moody diagram, and draw a relatively rough line, we get that it's on the other side of the wholly turbulent line, which proves that we do have a wholly turbulent flow in this problem. Continuing to part C, Part C stated, if the pump is 70% efficient, determine how much power must be supplied to the pump. So we know that efficiency is 70%, which means that eta is equal to 0.70. So the equation for this is eta is equal to power delivered by the fluid divided by the work of the shaft. And the power delivered by the fluid can be simplified into rho g q h p, which is HP is the head rise we have, divided by the work shaft. Now what we're trying to find is this. So simplifying this, we get that work shaft is equal to rho g q times head rise divided by eta. And all we did is we just cross multiplied to get work shaft on the top. So we know what rho is, which is 999 kilograms per meters cubed, times gravity, which is 9.81 meters per second squared, times q, which we found earlier, of 0.052 meters cubed per second. Now for head rise, we need to solve this separately. So I'm going to go here. So we have the equation, which is HP. Head rise is 20 minus 2,000 times q squared, which is 0.052 squared. And when we do this, you get HP is equal to 20 minus 5, which is equal to 15. So we write that as 15. And on the bottom, we have eta, which is 0.7 for 70% efficiency. And when we multiply this out and divide, you get that work shaft is equal to about 10.9 kilowatts of power. And that's all for this problem. Thank you.